So this is a presentation on Dirichlet energy minimization, and I'm going to be doing a thing called Sobolev Preconditioning. So really it's a presentation on both of these topics. So before we begin, I'd just like to discuss something that I've chosen to omit from the presentation, and that is a discussion of exterior calculus. In particular, the differential operator D comes up in a lot of the literature, but I've chosen to omit that so it will reduce the prerequisites of the presentation and will flow more naturally from content you're more familiar with. So the plan of attack for this presentation, and there's quite a few computations, so this plan of attack is so that we don't get stuck in the details too much. So number 1 and number 2 here, we're going to review gradient descent, and then I'm going to introduce gradient flows. And we're going to do this in finite dimensions. So this should be quite easy, these two topics. Then, next one is I'm going to really discuss what a gradient vector is. And this is a bit more tricky because there is a new definition for a gradient that I'm going to introduce, which is going to become important in the later sections. Then I'm going to introduce what functionals are, and at this point I'm going to introduce the Dirichlet energy. And then finally, we're going to use the insights we developed in step 3 about what gradients are to find the gradient of an infinite dimensional functional. Okay. And then I'll introduce Sobolev preconditioning. Okay, so let's start. So gradient descent is a classic algorithm for finding the minimum of some function given some initial position. So what we have is we have some function from Rn to R. For example, we have this curve here. And what we do is we pick some initial point in the domain, so on the x-axis. And then what we do is we calculate the gradient at that point. And then we make a step in the direction opposite to the gradient, recalling that the gradient points in the direction of greatest ascent. So by going in the negative gradient direction, we're descending down this function. And we iterate this procedure. We find the new point that we're at, find the gradient there, move backwards and repeat until we converge at some local minimum. Okay, so that's gradient descent, and what we're doing here is we're taking these finite steps and we're moving some amount, so we're taking these jumps. But what if you imagined we take smaller and smaller jumps, we take the limit as our jump size goes to 0, what's going to happen? Well, when you sort of continuize gradient descent, what you get is a gradient flow. So what that will be is you're given an initial position, x0, so same as before. But now what we say is our point here isn't jumping around in a discrete way, it's now going to flow along the x-axis towards the minimum, and the rate at which it's moving around is determined by the negative gradient. So the velocity vector, you could say, at a particular time is the negative gradient at that point. So at this point here, the velocity vector will look like this because the gradient looks like this. And as it moves around, eventually it will also find the local minimum after running for infinite time. So in the limit, that's where it will reach. Okay, you can see that here. So I'm just going to go through a quick calculation, an example, to really illustrate the point of a gradient flow. So we have this quadratic function from R2 to R. And we're given an initial point, 7, 3. Okay? And one thing you can try and do is you can plot the function f In fact, actually, I'll put a little plot on screen now of what this function looks like and where your initial point is. Okay, so what we're going to try and do is find a gradient flow from that point to a local minimum, and in this case that will also coincide with the global minimum, but we don't know that. So the corresponding gradient flow, if we take the gradient of this function f, what we get is we get 2x1 plus 2, and then we get 2x2. So this is what our gradient looks like. And you can see we've put our x1 gradient component here, and that's the time derivative of the x1 component, and we put the x2 time component gradient in here, and that's for this coordinate. Okay, so once we have this system of ordinary differential equations, we have two things we can do next. In order to actually run the flow forwards from our initial point, we can either solve the ODE numerically using quadrature, or we could actually analytically solve this ODE, since it's quite simple. It's like affine linear. So what you'll see, if you solve it, is that what we get this like classic shape. You know, you have your exponentials and your constant factors, and we plug in our initial conditions and you get some result. Okay, but what's important here is what happens as we either run the numerical solution for a long time and see what it converges to, or we look at our analytical solution and observe what happens when we take a limit as t goes to infinity. So for the numerical case, if we start at this initial point and we just run forwards the gradient flow, you know, our algorithm will start to converge to the value -1, 0. In the continuous analytical case, what we also find is that it also converges to -1, 0, as we should expect. Okay, so they're just two approaches to solve the system. Okay, so now a quick exercise for you, if you're interested, is to consider the following function, 5 sine xy plus y squared plus x, with some initial point, and I'll just plot right now what this function looks like on screen. Okay, and looking at the initial point, you can sort of potentially guess where the gradient flow should sort of rest at in the end. So what you could do is you could write down the gradient flow, you could write down the gradient, then write down the gradient flow, and then solve it numerically. So you're probably not going to be able to solve this one analytically. And then check your result. And you can check that just by sort of eyeballing it, making sure it looks legitimate, sits in the correct basin. Okay. So now we're on to the next part, which is distinguishing gradients and derivatives. So here's a question. If I have a function from Rn to R, what is the difference between the derivative of the function at a point x and the gradient of the function at a point x? And I'll give a hint. The gradient is defined in the following way, or at least it can be, in the case of the Frechet derivative. If you have f of x plus h, and you expand this out, you get some pattern that looks like this, and this linear operator a here, this is what we call our derivative at the point x. Okay. So the answer to this question, the difference between the gradient and the derivative, is more obvious when you see a concrete example. So let's just work through finding the gradient and the derivative of this function, f of x y is equal to x squared plus y squared. I'm just going to directly apply this definition here, and what we end up getting is we get this following expansion. So what you see is if we just match up what a is here, this is what a is, you can see that our derivative at the position xy is this row vector, you could say, or that matrix, 2x, 2y. And this is a linear operator, so that you can honestly think of this as a function. I think that's probably the best way to think of it, is it takes in vectors, and it evaluates, and it just does this matrix multiplication. So really, your derivative is a function, and our gradient is like you might be taught that this is sort of the transpose of this derivative, perhaps. However, doesn't this seem like a little bit arbitrary? You just take your derivative and find its transpose, or you sort of arbitrarily stack the partial derivatives in a column vector. It all seems a bit arbitrary. So one resolution to this is we can redefine what the gradient is in terms of our derivative. So the gradient, nabla(f) at x, is defined to be, or this is the new definition, it's defined to be the unique vector g in our vector space V. Oh, I should mention here, we've now just picked an arbitrary vector space V. We're not using Rn, but for the time being, you can just consider this Rn. So the unique vector g in the vector space V, such that the derivative at x evaluated at h is equal to the inner product between our mystical gradient vector and whatever h is, but this is true for every single h. Then we call that vector g nabla(f) of x. It's the gradient. Okay, this seems a bit mystical. So I just have a few points of why this is a better definition. So first of all, we can describe the derivative even when we have no notion of angle. However, we can't describe the gradient when we have no notion of angle, because we have to pick an inner product here. And an inner product, if you're unfamiliar, determines angles and lengths and things of vectors. So it also is the case that this definition, unlike the transpose definition or stacking column vectors, this one generalizes effortlessly when we look at infinite dimensional functions, or where our vector space is infinite dimensional. And so I also will claim that this is a very useful definition, because if you accept it, it will allow us to have the following trick, I guess, is you notice this inner product here has not been defined as any particular inner product. And what that means is we can actually pick whichever inner product we like. And so therefore our gradient vector depends on the inner product we choose in our definition. And it turns out that this is a very useful tool for speeding up gradient descent or gradient flows. And we'll see that later. It's called preconditioning. Okay. So let's take our new definition for a spin. Let's try an example. Okay. So looking at the same function we were looking at before, x squared plus y squared, we find its derivative, this row vector. I'll just quickly note here the three properties of an inner product. It's not, I should say three. The three properties of an inner product. You can look at these: symmetry, positive definiteness, and bilinearity. I'm just going to assume you're familiar with inner products. So here are two examples of inner products in R2, or in Rn in general. But we have our standard inner product, which is the one you're probably very familiar with. This is just like the dot product, where we take A transpose and multiply that by the vector B, and that's what we get. I claim that this second one is also a inner product, and it's an inner product with respect to a positive definite matrix A. You know, we can denote it something like this, and the way we evaluate this inner product is we do something like A transpose AB, where A is your matrix, and this is also an inner product. And what we'll see is when we define our gradient in terms of these two inner products, we get different gradients. Well, our gradient vectors look different. Okay. So let's first do the standard case. And if we write down our derivative, so this is df at xy, evaluated at h, okay, on the left-hand side. So that's what this whole thing is. And we're setting this equal to the inner product between g and h. Okay, and we're choosing the standard inner product. Okay, so this is, you can expand both sides looking at their definitions. And then you can figure out what the gradient, what the g vector will be, and therefore what the gradient is. So this, in this case, is 2x, 2y. Okay, which agrees with what we would have found if we just did it the normal boring way. Okay. So now let's consider a slightly more interesting inner product. Let's pick a arbitrary positive definite matrix A and slap that in between your G and your H vector in your inner product. Okay, same setup, D, F, X, Y, H, and then we have our inner product G, H, except now we're using a different inner product here. Okay, after shuffling things around and doing a little bit of algebra, what we get is that our gradient vector G is equal to A inverse, which exists since A is a positive definite matrix, transpose, times by this vector 2x, 2y. So in order to calculate the gradient, we need to invert this matrix A and take its transpose, and then we multiply it by this. So, cool. What does that matter? Like, sure, we have this new definition for a gradient, but how on earth is this useful? And we'll see on the next slide a very famous example where this is super powerful. Okay. So here's a really famous example of where we have picked an interesting inner product and it's given us a lot of magic powers. And so Newton's method is just this. It's the inner product with the A matrix, but instead of some arbitrary matrix, we're choosing to use the Hessian matrix. So what we're going to do is we're going to do gradient descent using the gradients that come out of the inner product with the Hessian matrix. Okay, so what happens is I'm just going to denote d squared f of x as the Hessian matrix of the function f at a point x. So what we do in Newton's method, we start at some initial point, pick some epsilon step size, set time to 0, we calculate the derivative, so the Jacobian and the Hessian. And then what we're going to do is we're going to invert the Hessian and take its transpose. So this is just what we were doing before, and then we also take the gradient, we take the derivative transpose. In this case, we can just do that very easily. And we get our gradient vector G. Okay. Then, in order to actually perform our gradient descent step, is we update our x position, is equal to our old position, and then we move a little bit in the negative gradient direction. Okay. So I claim that this is just Newton's method, and if you go and look online, you'll probably see one-dimensional write-ups of Newton's method, but this is an n-dimensional example. Okay. And so this is very, very widely used in numerical methods. Okay, so just a quick recap of what we've gone through so far. We've talked about gradient descent. We've spoken about gradient flows. We introduced a new definition for the gradient. And then we touched on this thing which I'm going to call inner product preconditioning. So where we're picking a different inner product to sort of get new kinds of gradient descent out. Okay, so where are we going to go next? Well, in the chapter that we just did, all we were doing is we were minimizing functions from Rn to R via gradient descent or gradient flows. But what if instead of Rn, our function's domain is something infinite dimensional, so like a function space. So now, this is what the next part of this presentation is going to all be about. It's about minimizing functionals which are just functions from an infinite dimensional space, to the real numbers. Okay. So, first of all, what does a gradient flow look like in a function space? So, if you pick and I'm doing air quotes here, point in a function space, that corresponds to, it is an entire function. Okay, so what you see here is a point, or it's an element of this function space. Okay, and let's say we have some map E from our function space to the real numbers. Okay, so I plug in a function and it gives me out a real number. Okay, so if I plug in this function, I get the number 124. So a gradient flow in this function space, what it does is it will smoothly transform my initial function through time to some final function, all the while reducing my functional. So all while reducing this number here. So perhaps this function was measuring something like the squiggliness of this function. Okay, and as we get smoother and smoother and smoother, the functional goes down and down with time. Okay. So what I'm going to introduce is the Dirichlet energy functional. So this is the functional we're going to look at in the presentation. There are lots of other really cool ones, but this is just the easiest. Okay, so we have some function space that maps, well, we have a functional E, Dirichlet energy, that maps from a function space to the real numbers. And so we have functions which have domain omega, and they have some codomain. Okay, and what this Dirichlet energy does, the way it works, it takes our function and then it integrates the gradient of the function over the domain. Okay, and just point out one thing, this will come quite important in some calculations later. We're just going to assume that our domain omega of our function f has no boundary. Okay. So if you've been paying attention, you might actually say something like, oh, well, what gradient is this, since now our gradients depend on inner products, or something like that. And I'll just pause you. This is almost always the standard gradient, unless someone says otherwise. So if you see like nabla f of x, they're probably referring to the standard gradient. So you can safely assume it's that here. Okay, so what does this Dirichlet energy measure about a function f? Well, it measures how variable or wiggly a function is. So if our energy is larger, then basically what we're saying is that the gradient is very large for this function. And when the energy is smaller, we're saying that the gradient is smaller. So when it's large, it might look like something like this. If the gradient was small, our function might look like something like this. Okay, so they're the two sort of characteristics. Okay, so here's the question. Given some initial function with some initial energy, can we do something akin to gradient descent or a gradient flow to minimize our energy? And I mean, why would you be watching if the answer was no? The answer is yes. So, before we get into actually designing a gradient flow on this energy, we're just going to need to do some basic algebra to get it into a more amenable form. So our energy functional is defined this way. Okay. And what we do next is we rewrite this inner bit as an inner product. This is just a standard Euclidean inner product. Then we apply Green's theorem, or like it's a generalized version of integration by parts. And then we use the property that the boundary of omega was 0, as we decided. So, this is only true because we just defined our functions this way. And then what we can do is we can write this whole expression here as an inner product itself. Okay, so this final step's a bit weird, but it's just a functional inner product. So given two functions, we can define the L2 inner product of those two functions as the following integral. Okay, that's certainly something you can do. And it's perhaps a task to check or prove that this is an inner product according to the definition. Okay, so what we really end up with is we end up with the statement that our energy functional is the inner product between the negative Laplacian of f and f itself under the L2 inner product. Okay, so with this setup, we're now ready to find the derivative of our energy functional. Okay, so how do we do that? To find the derivative of our energy in some direction eta, what we can do is we can consider some function at some point f, and then we take some small direction. I guess direction here is like another function, and we add that a small amount of our function eta. So epsilon you can assume to be something small maybe. Okay, so if we do this and we expand out, we use some properties of the Laplacian and then the bilinearity of inner products. Eventually what we get is we get to some expression that looks like this. We have the left-hand side is equal to the energy of f plus this inner product here plus some remainder term. Okay, now if you recall, the definition of the derivative matched up very closely with this. We took some vector and we added some small other vector, and we would get something that looks like this. So our derivative of our energy at f is a function which takes in some directional vector, and what it does is it evaluates this inner product on the function eta. So we're ignoring the epsilon. It's not actually crucially important here. So yeah, this is the derivative of our Dirichlet energy. At this point, it's all very abstract, but if you go with this, we will be able to eventually find a gradient. So we have our derivative, we'll find a gradient, and then we can find a gradient flow. Okay, so this is the derivative of our Dirichlet energy. All right, so now what we want to do is we want to take our derivative and we want to now find a gradient. And here's where we can use our special definition of a gradient vector. Okay, so remembering that the gradient g at f is the unique, and in this case it's a function, it's the unique function such that the derivative of the energy at f evaluated at eta is equal to the inner product between g, our gradient, and eta, and this needs to be true for every single eta. Okay, so what this is, if I just rewrite the derivative as what we found, what we need to, in order to find the gradient, we first pick an inner product, and then we solve to see what g has to be to always make this equality true. Okay. So some few natural choices for what inner product we should use. Well, the first one is this L2 inner product, which is I introduced earlier, and that's just integrating the inner product of the functions over their domain. The second one is this H1, which is Sobolev inner product. And what we're doing here is we are integrating the gradients of, or the inner product of the gradients of the functions over the domain. And you have H2, which is like the Laplace operator of our functions, inner producted over the domain, and so on. Okay. So we're really going to explore these three examples. So the first one is an inner product on L2. So this shouldn't say L1. Yep. Okay, so what happens if we pick this inner product? Well, we have our derivative on the left-hand side. And then on the right-hand side, we have our G eta inner product with our L2, which is what we've chosen. Okay, just by looking at this, it's plain to see that G is equal to negative Laplace F. If you just place that in here, the left and right hand side are identical. So there you go. Okay, so the gradient of our Dirichlet energy E at the point F with the L2 inner product is negative Laplace F. Okay. And we can convert that into either a gradient flow or a gradient descent. So if we convert it into a gradient descent, we start at some initial function, f0, and we pick some step size. And what we're going to do is our iterative procedure is going to be to choose the next function to be the previous function, and then we move in some direction opposite the gradient vector. Okay, so negative the direction of the gradient. And if we consider a gradient flow, we start at some initial f0 function, and then what we're going to do is we're going to say that the rate of change of this function in time is going to be equal to the spatial derivative, the spatial, like the Laplace operator applied to f. And this Laplace operator is on the spatial dimensions of f, not on the time dimension. Okay, and this is exactly the heat equation. So if we now just think about what this does to a function, if we start with something really squiggly, okay, this is our f0, and then we run this PDE, we run this gradient flow, what's going to happen is you can sort of imagine these being temperature values or something, and it all sort of smooths out. So over time, it's going to look something like that, right? Your bumps will sort of smooth, and that's what the Laplace operator is allowing us to do. Okay. So the next one is what happens if we pick a different inner product. Here, let's pick this H2 inner product. Actually, I think I should say H1. Yep. Okay, so we pick this H1 inner product, and the way that's defined is it's defined using, it's an inner product of gradients of your functions. Okay, so what you can usually do is if you have some other inner product, you can often rewrite this inner product as some other inner product. So we have our H1 inner product, and we're going to rewrite it as that L2 inner product. We're going to do the following process. So the H1 inner product, we have this definition here. Write it out. Then what we're going to do is we're going to apply Green's theorem. And then we're going to use the fact that the boundary of omega is 0, so this is going to disappear. So we're just left with this. And then pull this negative sign in, and we're left with an L2 inner product on these functions. Okay, so now putting our definition of like the gradient, so we say that the derivative of the energy at a point F, evaluated eta, is equal to this, and that is set equal to our inner product, G eta. Okay, future Michael here, I just want to address this point. When you have a function, Hi, future Michael here. I just want to address this point really quickly. So if we had that f was our gradient, then we could also consider like f plus phi is equal to g, with the condition that Laplace phi is equal to 0. And the reason why is that if we apply the Laplace operator to both sides, like this, then what we end up getting is this phi will actually disappear. So we get Laplace f equals Laplace g, and then you can multiply both sides by -1. So this is also a solution. So you just need to account for this. This is why it doesn't work. Yeah, thanks. H1. So now what we're going to do is we're going to use what we just calculated in this box to replace this right-hand side. Okay, so now, in order for this left and right-hand side to be equal, we need negative Laplace f equal to negative Laplace g. Okay, I'm going to do something a bit sus here, and that is going to be, I'm going to like invert the Laplace operator. You actually, like in practice, need to do a little bit of weirdness, like adding some small amount to allow this to happen if you're solving this numerically, but for all intents and purposes, let's just go with it, okay? So, hi, future Michael here. I just want to address this point really quickly. So, if we had that f was our gradient, then we could also consider like f plus phi is equal to g, with the condition that Laplace phi is equal to 0. And the reason why is that if we apply the Laplace operator to both sides, like this, then what we end up getting is this phi will actually disappear. So we get Laplace f equals Laplace g, and then you can multiply both sides by -1. So this is also a solution. So you just need to account for this. This is why it doesn't work. Yeah, thanks. We invert the Laplace operator and it's going to cancel with this left-hand side. And eventually what we're going to get is we're going to get f is equal to g. So our gradient vector is equal to function f. And this is not super weird. So in Rn, it's like saying that the gradient of some function f evaluated at x is equal to x. That's basically what this is saying. So, or it's something akin to that, okay? Now, so the gradient of our energy at the function f with the h1 inner product is just f. That's it. And so if we write our gradient flow down, so the time derivative of f is equal to, when we're moving in the negative direction of the gradient, so negative f of t. This is our gradient flow in the h1 inner product. Okay. And finally, let's look at my final example, which is the h2 inner product. Okay, and I'm just going to sort of speed through this. Here's your definition. It's got the Laplace operator in it. So we first write out, we're going to do a similar thing to what we did before. We're going to eventually write it down as an L2 inner product. So we write down our H2 inner product, apply Green's identity here, integration by parts basically. We cancel this because it will be 0 since we're integrating over that empty set. We apply integration by parts a second time. Again, we use the fact that we're integrating over an empty set here. And so we get this. And finally, you can write that as an L2 in the product. Okay. So what we get is we can write the H2 in a product between a function g and a function eta as Laplace squared g and eta, but L2. So again, we write down our definition of a gradient. Left-hand side is the derivative, right-hand side is our inner product. We place our definition of our inner product. Well, we use our thing we derived here to rewrite it like this. And now we can identify the left and right-hand sides. So we have negative Laplace f is equal to Laplace squared of g. What you can imagine doing, again, this is questionable, but you can imagine like applying the inverse Laplace operator twice to f. And so we get something that looks like this. So therefore the gradient of our energy at a function f with the H2 inner product is this thing here. It's the negative of the inverse Laplace operator evaluated at f. Okay. And so therefore our gradient flow, our derivative with respect to time of our function f, is equal to the inverse Laplace operator applied to f. Okay. So we have 3 inner products, and that gave us 3 different gradient flows. And I like to stress they all minimize your Dirichlet energy. So you start with some initial function and you run these gradient flows. All these gradient flows will be minimizing your energy, or they'll take you to a local minimum at least. Okay. So here they are. So our L2 gave us this like heat equation looking thing. This H1 inner product gave us this ordinary differential equation. This will be important in a sec. And our H2 inner product gave us this other thing with an inverse Laplace operator. Okay. So my question to you, think critically. If you wanted to actually implement this in computer code, if you actually wanted to minimize the Dirichlet energy of some function, which of these gradient flows would you choose? Which of these would like spare you headaches? Well, these two here, the first and third ones, these are both partial differential equations and require you to like evaluate this Laplace operator on your function. And you can actually prove that this is computationally a harder task than this second option here, which is just an ordinary differential equation. So for me personally, I would definitely go with this option here. Okay, and I'll give you some intuition about what are the differences between these gradient flows, like if you had to visualize what they did to an initial function. Well, our first equation, which is like the heat equation, we start with some function, and what it does is it very quickly will smooth out the high frequency jitters in our function. So you can see here it smoothed it out. So it smooths out the high frequencies very quickly, but what it struggles to do is it actually struggles to flatten out the function completely. So it doesn't really flatten out your low frequencies. Okay, and I'll jump over here to our third one, and I'll come back to a second. What that does is we start with some initial function, f0. We run our gradient flow, and after a very short amount of time, you'll get something that looks like this. And so what it's doing is it's very quickly flattening out the low frequencies, so it's taking this curvy shape and it's flattening it out. But what it fails to do is it fails to flatten out the high frequencies. So you can see that quite visually here. Okay, and this final option is somewhere in between. And so what it does is it smooths out the high frequencies at a moderate rate as well as smoothing out the low frequencies at a moderate rate. And so in some sense, this is better than these two gradient flows because it's going to converge towards like what we would consider a better solution faster. Okay, so in the limit, all of these will converge to the same thing, but this one in some sense is going to get closer to what we think is the actual limit faster. Okay, so really that's the end of the presentation, but here are some like ideas on what to look at next. So first of all, you could ask the question, how do we quantify what it means to pick the best in a product? Is it really heuristic driven and like arbitrary, or is there some fundamental principles? And the answer is there is some specific choices you can make that finds some notion of the best one. Next question is, what is qualitatively different about using different inner products? Can we actually quantify this notion of like high and low frequency smoothing in a specific, precise way? And of course, this is maths. The answer is yes. The third question is, what are some cooler energy functionals? So we looked at the Dirichlet energy, which was just measuring the squiggliness of a function. But there are some really awesome examples online. And for example, you can look at this thing called the tangent point energy. And Keenan Crane has some excellent articles and YouTube videos showing tangent point energy minimization, which is related to unraveling knots, or can be used to unravel knots in space. And so finally, what if we consider energies of surfaces rather than curves? This really isn't a big generalization at all, but right now we were just considering our energies evaluated along a curve. But what if we had a Dirichlet energy of a surface? So it's measuring like the squiggliness of a surface, and then we could run something like a gradient flow for an entire surface rather than a single function. And that's not too hard to generalize to. So yeah, thanks for watching. I hope you enjoyed this presentation on Dirichlet energy minimization. Yeah, thanks.